In section 1.8, we're going to work with solving real-life problems involving right triangles. We're going to be working with directional bearings, and we're also going to be working with harmonic motion. Okay, so we're going to start off with applications that involve right triangles. And when we talk about solving a triangle, so when it says to solve a triangle, that means you're going to be supplied some information and you need to identify all of the unknown sides and unknown angles. So if you remember, or you should remember, that we'll have angle A and we'll have side A. A is opposite, side A is opposite angle A. Angle B and the side opposite, and angle C and the side opposite. Now C, it's a right triangle. C is 90 degrees. You can see angle A is 20 degrees, and they've given me angle B, which is 15 degrees, or sorry, 15 units. Doesn't say degrees, obviously, it's a side. So if I want to go through and solve this, I'm going to use the trig functions that we know, the three main trig functions, sine, cosine, and tangent, to do that. So for starts, if I've been given two angles, I can always find the third, because the sum of the angles in a right triangle is 180. So that means that this must be 70 degrees. These two add up to 90, and this one's 90, so it's 180 degrees. And then once I go through trying to work with the parts that we don't have, I know that the sine of 70 degrees will be equal to the side opposite over the hypotenuse, which is C. If I multiply both sides by C, and then divide by the sine of 70 degrees, then I will be able to get my answer. So I'm going to pull out my handy-dandy calculator. I'm going to do 15 divided by 70 sine equals 15.96. Okay, so this is going to be 15.96. And then if I want to find A, right, A is the side opposite 20, or I could say A is the side adjacent. I think I'm going to use 20. I know that the tangent of 20 will be equal to A divided by, right, the side opposite over the side adjacent, A divided by 15. Now I could have done tangent of 70 degrees is 15 over A, but I like to put my variable in the numerator when I can. So if I multiply both sides by 15, I get this, and I go, okay, let's do it. 20 tangent times 15 equals 5.46. Okay, 5.46. And now I have all of the different parts of my triangle. In this problem, I've got a descriptive, and I'm going to be drawing a picture that will make a triangle. So I've got a house. So let's say this is my house. Right? I've got a house, and I've got a ladder that's 16 feet long. So a 16-foot ladder is there. The angle of elevation of the ladder, that's from the ground up, this is 80 degrees. Find the height of the top of the ladder to the ground. Okay, so I've got the hypotenuse, I've got an angle, and I want the side opposite. Sine is going to work really well for that. The sine of 80 degrees will be the height of the side opposite divided by 16. And if I do 16 times the sine of 80 degrees, that will give me the height. I go back to my calculator, and I do 80 degrees sine times 16 equals, and it's 15.76 feet. Okay, so my height will be 15.76 feet. Okay, pretty straightforward work. Here's another similar problem at a point 65 feet from the base of a church. So here's a church. And there's a spot up here, and this is 65 feet. Oh, okay. And then there's a steeple, right, a church steeple, so maybe there's a tower, blah, blah, blah. There's another steeple. And I have a different measurement there. Okay, at a point 65 feet from the base of a church, the angles of elevation to the bottom of the steeple and the top of the steeple are 35 degrees, is there, and this larger angle is 43 degrees. Respectively, find the height of the steeple. Okay. And I realize in looking at this I've labeled it wrong. The point 65 feet from the base is here. This is 65 feet here. Okay, so I know that I can do the sine of 35 is equal to the height over 65. So 65 times the sine of 35 will equal the height. So 35 sine times 65 equals, so that's going to be 37.28 feet. Okay, so 37.28 feet. And then I can also measure this distance, right? So that's this distance here. I can measure this distance here by doing the same calculation with the sine of 43 degrees. So if I pop in and I do 43 degrees, sine times 65 equals, I'll get 44.33. Okay, so this is 44.33. And then the steeple will be the difference between the two. So it looks like the height of the steeple is 7.05 feet. So here's another word problem that we want to take a look at. If I have an airplane that's 100 feet high, so here's 100 feet above the ground, and 1,600 ground feet from its landing area, 1,600 feet, determine the angle of descent in degrees. So now they give me two different sides and they want to find theta. I know that the sine of theta is going to be 100 over 1,600. That's going to be 1/16. So if I go back to my calculator and I do 1 divided by 16 is equal to that. And then if that's the sine and I want to know the angle, I use the inverse sine function. And the answer is 3.6 degrees. Okay, so theta is equal to 3.6 degrees. The key in all this is making the appropriate triangle. So you notice in each of these last problems, the first thing I did was I sketched out the situation to create a right triangle. Now when we're talking about surveying and navigation, directions can be given in terms of bearings, and bearings measure an acute angle that creates a path or a line of sight with basically on compass points. So if you're talking about south 35 degrees east, that means I'm at east and I go south 35 degrees. I'm sorry, 35 degrees from the y-axis, right? So you go due south and then you move 35 degrees toward the east. Okay, so my mistake in how I described that. This would be north 80 degrees west. This would be north 45 degrees east, and you can see that each thing creates a slightly different type of angle. So if we want to do a problem like that, when we start looking at bearings, a ship leaves port at noon and heads due west at 20 knots, which is 20 nautical miles per hour. Okay, so it started here, and it headed due west at 20 nautical miles per hour. Right? At 2 p.m., okay, which means it's traveled 40 knots, 2 hours at 20 knots per hour, right, would be 40 miles, nautical miles. At 2 p.m., the ship changes course north 54 degrees west. So you see they've moved 54 degrees here, which is helpful to us because we know then that this would be 36 degrees. Okay, because we're probably, if you look at these triangles, we're going to work with the right triangle, we're going to work with this one. And that's going to be 36 degrees. Find the ship's bearing and distance from the port of departure at 3, which means what we want to find is this angle here. Right? And if we think about it, we know that the answer is going to be north, some amount of degrees west, right, when we find this. So what types of things can we actually figure out at this point? That's going to be part of our problem. So we're going to need to try to figure out this item. Okay, so we know that we've got this item here, which is helpful. We've got this item here, which is crucial. So in this triangle, I've got the hypotenuse. It's 20 nautical miles, right? Because it traveled for an hour at 20 knots. So that's how we know this is 20 nautical miles. So that means I could use the parts I'm going to need to determine this is I'm going to have to find this D value, and I need to find this B value so that then I can go ahead and calculate this out. So if I work now, I can do that the sine of 36 would be B over 20. So if I do sine of 36 degrees equals B over 20, if I multiply both sides by 20, I'll get that B is equal to 20 times the sine of 36. So we'll go back to our calculator. We do 36 sine times 20 equals, and it's 11.76. Okay, so B is equal to 11.76. That's over here, 11.76. Well, then I also know that the cosine of 36 would be equal to D over 20. So if I do 20 times the cosine of 36 degrees, that would be equal to D. So let's figure out that. Right, so I do 36 cosine times 20, and that's 16.18. So 16.18 is equal to D. 16.18. Okay, that means that this whole length here is 40 plus 16.18, so that whole amount would be 56.18. And I know this, so I know the side adjacent to my angle, and I know the side opposite my angle, so I know that the tangent of the theta that I'm looking for is the side opposite, 11.76, divided by the side adjacent, which would be 56.18. So if I go back now to my calculator, I'm going to do 11.76 divided by 56.18 equals, and that's the tangent. So if I use the inverse tangent, I'll find the angle. It's 11.82 degrees. So in this case, theta is going to be 11.82 degrees. So the bearing is north 11.82 degrees west. Nope, I lied to you. Right? It can't be that because that's this angle, but the angle we want is this. So we'll have to do 90 minus 11.82. This is going to be 18. 9 minus 1 is 8. And 8 minus 1 is 78.18. So my mistake. 78.18 degrees. Right? So remember, I found this angle, but that's not the angle for the bearing. The bearing always comes off of the y-axis. Okay, if we work with harmonic motion, we can track, if we look at an item that is stretching a spring and compressing a spring, and I graph its height over time, that will be modeled by a sine or a cosine curve. Okay, so when we take a look at a problem like this, I can see that I've got my center here, and it will go up 10 and it'll go down 10. That means my amplitude is 10. That's good. And from it going from, so it goes further that the time it takes for the ball to move from its maximum displacement above 0, up here, to its maximum below 0 is 4 seconds. So from there to there, 4 seconds. So if we think about a sine curve, right, it does this. This distance from here to here is 1/2 the period. Okay, so that means that my period is 8 seconds long. Okay, and if I have the amplitude and the period, I can write the function. Okay, so let me go ahead and do that. Remember, this would be y is equal to the amplitude, 10 centimeters, times, we'll say sine, because it starts at 0, right, of, right, I know that 2 pi divided by b is equal to 8 seconds. So 2 pi divided by 8 seconds would be equal to b. So b would be pi over 4, right? So pi over 4x. This would be the function that would do that. Okay, so if we continue on taking a look at this, find a model for a simple harmonic motion that follows these conditions. D is equal to 0 when t is equal to 0. That means it's a sine function, right? Because that's where we start at 0. The amplitude is 6 centimeters, and the period is 3 seconds. So I know it's going to be y is equal to 6 times the sine of something. So I have to figure out what b is. I know that 2 pi divided by b is equal to 3 seconds. So 2 pi divided by 3 is equal to b. Multiply both sides by b, divide both sides by 3 seconds. So this is going to be 2 pi over 3x. Right, then find the frequency. Right, the frequency is the inverse of the period. Right, so my period was 3 seconds. My frequency is 1/3 of a second. Okay, so that's just going through this particular problem. Right, if we take a look at another problem like that, here they give me the equation. Find the maximum displacement. Well, maximum displacement is 6, the amplitude is 6. Find the frequency. Okay, well that's the inverse of the period. So the period is going to be 2 pi divided by 3 pi over 4, which would be 2 pi times 4 over 3 pi. Pi's will cancel. I'll have 8/3. That's the period. So that means the frequency is the inverse of that. It's 3/8. What's the value of d when t is equal to 4? Okay, so when t is equal to 4, I have d is equal to 6 times the cosine of 3 pi over 4 times 4. Well, these will cancel. I'll just get 6 cosine of 3 pi. Well, if you think about the cosine of 3 pi, right, 2 pi is all the way around the circle, 3 pi is one more around. Cosine is the x coordinate. That's -1, 0, so d would be equal to -1. Oh, I'm sorry, -6, because I have to multiply it times 6. Okay, and the least positive value of t for which d is equal to 0, well, it's cosine, right? So I know with cosine, it starts up here. They want a positive value, but the first quarter of the period it goes down. That's where it's going to hit 0. If my period is 8/3, if I divide that by 4, 8/3 times 1/4, that would be 2/3. T is equal to, 2/3. Okay, so that's it for this section. We worked on real-life problems solving using real right triangles. We talked about the definition of bearing. Remember, we're always measuring angles from the y-axis. Okay, when we're talking about bearing, and so we've stated the definition of bearing, and we went through simple harmonic motion.